Great. Thanks a lot. Oh, go ahead.
Sorry. We have rules and regulations. Before we start, we're very delighted to have our own Luca Iliesiu talking to us about supersymmetric indices from the gravitational class.
Great. Thanks for the invitation. So this is work done together with Joaquin Tirashi, Murat Kaloglu, Samir Murthy, and Jan Boru, who's in the room, who's my grad student. So feel free to ask him questions afterwards. He knows a lot more than I do about all these topics. So let me start with by saying that one of the most celebrated results in string theory that we know of is that we've reproduced the entropy of black holes by using a string theory count. So this is an important physical result, but it also had a lot of beautiful mathematical consequences. It led to a more in-depth study of modular forms. It led to a better understanding of phenomena such as wall crossing and many different things. So it's worth digging more into it. So let me make this statement more precise about what people actually did. And this is the most famous equality was first derived by Strominger and Vafa. What they actually did, and what most subsequent other papers actually did, is that they computed a string theory index. So the string theories that they were studying were supersymmetric, so they had an associated supersymmetric index. So this was computed at weak coupling. Essentially, you can do this computation in a free theory. And they found that this correctly reproduced the area of an extremal black hole. In a sector of fixed charge. Okay, so there are three problems with this equality that we should be discussing. The first problem is that on the left-hand side, it clearly says that we're computing a supersymmetric index. Well, on the right-hand side, the area of a black hole is supposed to capture its entropy. And it's supposed to, since the black hole is extremal means that the temperature of the black hole is 0. So it's supposed to capture the entropy associated to a degeneracy, so just the log of a degeneracy. So problem one is that the right-hand side, sorry, left-hand side is defined at any temperature. And counts fermionic and bosonic states with an opposite sign. That's because an index has a -1 to the f insertion. And more importantly, it's a protected quantity. On the other hand, the right-hand side is only defined as t equals 0. And has no -1 to the f insertion. And it's also not protected. So why are we matching a quantity that's protected to something that's not? And in fact, there was this misconception that in ADS-CFT, this equality doesn't actually hold. In the following sense, that if you compute an index on the boundary side, let's say in n equal 4 super Mills, that it doesn't actually receive contributions from black holes. And I'll talk about that misconception in a second. The problem number two just relates to the right-hand side of the equality, and it's this word area. So there's this assumption that the area of the black hole, even in the extremal case, correctly reproduces its entropy, perhaps we should question that. In the past couple of years, what people have found is that as the temperature, if you take the temperature of a black hole to 0, the situation is quite surprising, even though effective field theory, so let's say the gravitational theory that describes the black hole, is still valid. What happens that as you take the temperature to 0, quantum corrections in the metric and in a bunch of other fields in your effective field theory could blow up. In other words, what happens at exactly t equals 0, and this was actually something found by Sen, is that there's a set of deformations of the metric. G mu nu goes to G mu nu classical plus H mu nu, 0 mode. There is some set of H mu nu that if you plug into your effective action, they keep your effective action completely unchanged. So in other words, there's like an entire moduli space of metrics that all have the same actions in the extremal limit. And therefore, there's this piece, the classical piece of the metric is not entirely trustworthy. And when we talk about the area of a black hole, we compute that using the classical metric. So we should be very careful about trusting this equality when we really approach extremality. Now, what happens in practice is that we found that for non-supersymmetric black holes, this inequality becomes invalid as the temperature goes to 0, while for supersymmetric black holes, this equality remains valid as the temperature goes to 0, but I won't go into that. So, studying these systems at finite temperature, you could better actually understand what's the actual degeneracy of the black hole. But even if you do that, there is a problem, which brings me to problem number 3. Even if you understand what happens for a single extremal black hole in the limit t goes to 0, there's still a question with what happens to more complicated geometries that are supposed to contribute to the index. So for instance, in some situations in string theory, the index doesn't receive this equality, doesn't receive contributions from only a single black hole. It receives contributions from an arbitrary number of multi-center black hole configurations. So for example, multi-center black holes. And while you might be able to study what happens to this relation for a single black hole by perturbing the metric and exploiting some of the symmetries that the black hole has, when you have a multi-center black hole configuration, the situation is more complicated because most generally you can't even put it at finite temperature. These multi-center configurations typically only exist because the electromagnetic force and gravitational force exactly cancel each other. If you turn on a temperature a little bit, typically what happens is you increase the mass of the black hole while the charges remain fixed. And therefore, like the system usually collapses. So there are no static solutions generally that describe these multi-center configurations. So how would you even define this procedure of taking the temperature to 0 and seeing what happens to the 0 modes that exist at exactly 0 temperature? And there's not only the problem of multi-center solutions, there's other solutions such as the attractor solutions. Black rings, SUSY black rings, and many, many others. So my purpose today is not to explain how to regularize things or why this equality is true as the temperature goes to 0. It's to replace the right-hand side of the equality, not by the area of a black hole, but by an actual index computed using the gravitational path integral. So the thing that I will answer today is a general procedure of how we compute an index using the path integral, the gravitational path integral. Okay. So first, because there might be people in the room that have never even studied the gravitational path integral, let me just summarize what's the procedure to compute a simpler quantity, the partition function of a black hole. So first, let's do the partition function. And studying the partition function will also let us understand problem number 1 and why people thought in the beginning of ADS-CFT that indices don't really have anything to do with black holes incorrectly. So to compute the partition function, what we want to compute in a quantum mechanical system is z of beta equals to trace over some Hilbert space of e to the minus beta h. And what we usually do to compute this at a path integral level is that we make the time circle in our field theory be periodic. So we work in Euclidean signature and make the time circle be periodic. In gravity, the situation is a bit more complicated because we can only specify things through asymptotic boundary conditions. So Gibbons and Hawking explained that basically the prescription that works in field theory to make the time circle periodic perhaps also works in gravity, where we just impose that at the asymptotic boundary, the time circle is periodic. So the procedure is to take whatever gravitational solutions we're studying, weak rotate it to Euclidean signature, and try to find geometries that asymptotically satisfy the boundary condition that tau is periodic as tau plus beta. So let's take the example of a black hole. It could be a Schwarzschild or a Reinster-Nordström black hole. The general form of the metric takes the following form. So we want to fill in this geometry in such a way that it satisfies this boundary condition and has this metric, and make sure, because we're in the gravitational path integral, we're weighing things by the Euclidean action. So z of beta is the path integral over all metrics computed with these boundary conditions. We want to evaluate this path integral by saddle point in the limit when 1 over g Newton is very large. So we don't want our action to receive any contributions from singular points. And therefore, we need to make sure that the manifold is smooth. In particular, we should make sure that as we reach the horizon of the black hole, that's the location where f vanishes, for metrics of this form, that we encounter no conical singularity. So in order to make sure of that, we can just expand this form of the metric out. So it looks like f prime, r horizon, times delta r, d tau squared, plus d delta r squared, over f prime, r horizon, times delta r, plus the spherical component of the metric. And I can just do a repair. So here, r, I'm just rewriting it as r horizon plus delta r and expanding for delta r much smaller than rh. And I can do change of coordinates in this near horizon region such that this delta r looks like f prime of r plus over 4 times some new coordinates rho, and tau tilde, I'll just rescale it by some factor of beta that appears on the boundary, such that tau tilde is 2 pi tau over beta. Tau tilde is now, using these boundary conditions, tau tilde is now 2 pi periodic. And the metric, after this change of coordinates, just takes the following simple form: beta squared f prime of our horizon squared divided by 16 pi squared rho squared d tau tilde squared plus d tau tilde squared plus the spherical part of the metric. So this looks exactly like 2D flat space that could potentially have a conical singularity if this coefficient is not exactly equal to 1. Right? So here the geometry looks.
Sorry, can you read off and it's a little hard to see?
Sorry?
Can you read off and roll
Yeah,
off?
it's beta squared f prime of rh squared 16 pi squared, and then this piece is rho squared d tau tilde squared plus d tau tilde rho squared. So it's exactly like the polar coordinates in 2D flat space, where I can have an arbitrary parameter in front of rho squared d tau tilde squared that could in principle introduce a conical singularity in 2D. So in principle, at r equals rh. Hmm? Oh, sorry, d rho squared. My bad. Yeah. Sorry. So in principle, we run the risk that at r equals rh, we have a conical singularity unless we make this coefficient to exactly be 1. So if we make this coefficient exactly be 1, then the space-time is smooth, and this actually fixes the temperature of the black hole as a function of f of r. F of r is in turn determined by the mass and charges of the black hole, so it completely fixes what the temperature of the black hole is in terms of its parameters, and it tells us that this is the leading contribution to the path integral. Namely, if I want to evaluate z of beta in a saddle point approximation, so saddle point, when 1 over g Newton is sent to infinity, this is just given by, at leading order, by e to the minus Euclidean action evaluated on this black hole metric. Okay, so this sets beta as a function of the parameters, but it also tells us something else. It tells us that if this saddle dominates, which is an if, but if this saddle dominates, it tells us that the time circle, which is periodic at the asymptotic boundary, becomes contractible in the bulk. So now let's look at an index. So an index is just the trace of e to the minus beta h with a minus 1 to the f insertion. Let's say that it's in a sector of fixed charge. So I might have some R symmetry. I might have some additional gauge fields. I can fix everything except the angular momentum of the black hole, which is weighted by this factor of minus 1 to the f. So first, let me tell you what we expect from a general theory of a general supersymmetric theory, quantum mechanical supersymmetric theory. Well, if the theory is supersymmetric, then my states arrange themselves into supermultiplets. And the properties that these supermultiplets have, if H, for instance, is the anticommutator of two supercharges, is that only states that are annihilated by Q contribute to this quantity, but states that are annihilated by Q have H equals 0 from this relation. So therefore, only states with H equals 0 contribute. So this index should just capture the difference between the difference between the bosonic degeneracy of states that are annihilated by Q and the fermionic degeneracy of states that are annihilated by Q. So it should capture this difference. This is just what expectation we have from the quantum mechanical side. Sometimes on the quantum mechanical side, this relation is modified when the superalgebra is extended. On the left-hand side of this relation, I might also have R-symmetry terms. So sometimes, and this will happen in the talk today, instead of H appearing by itself, H minus R appears, in which case this difference between dB and dF is simply multiplied by the relevant factor of R charge. So essentially, it's not only states that have H equals 0 contributing, it's states that have H equals R, but if I fix the R charge, then essentially that only gives a Boltzmann weight, multiplicative Boltzmann weight for the degeneracy, the difference in degeneracy between bosonic and fermionic states that are BPS. So BPS means that they're annihilated by Q. So now let's go to this geometry. And let me explain why people in the early days of ADS-CFT thought that there would be no contributions to the index. So according to Gibbons and Hawking, this trace gives us a prescription for what boundary conditions we should set for the gravitational theory. So -1 to df at a path integral level, what it does is it changes the periodicity of fermionic fields as they go around the thermal circle. So the trace without the -1 to df insertion has fermions be anti-periodic around the thermal circle, and with the -1 to df insertion, they should be periodic. So index is equal to periodic fermions. So then if you look at this figure, if you make the fermion periodic around the thermal circle, it means that a fermion is periodic around the contractible cycle, which means that there's actually no valid spin structure that you could associate with this manifold. And things break down. Therefore, people suggested, even in the first, I think, second ADS-CFT paper, people suggested that these geometries simply don't contribute to an index. The only thing that contributes to an index are geometries where this cycle is not contractible, namely thermal ADS with a periodic fermion propagating around the thermal circle. So that turns out to be incorrect for the following reason. We haven't actually tried to find all the geometries that actually fill in this geometry, fill in these boundary conditions where the fermions are periodic on the boundary. So let's take a slightly different perspective and view -1 to df. The two perspectives will be completely consistent with each other. But for now, let's view -1 to df not as a change of boundary conditions for fermionic fields, but instead, let's write it more suggestively as e to the 2 pi I j, where j is, let's say, the angular momentum generator on this geometry. So if in a partition function, one puts additional factors of e to the mu times some conserved charges, q, then the boundary conditions that this imply on the gravitational side or on the field theory side is that at asymptotic boundary, we have to turn on non-trivial holonomy for the gauge field associated to Q. If we turn on a prefactor in front of J, then essentially we're fixing something like a chemical potential for the angular momentum of the system, which, in other words, is fixing the angular velocity of in the system. So this 2 pi ij is like the angular momentum of j, which by definition is like angular velocity times beta. So this tells us that the geometry that we should be looking at to satisfy these asymptotic boundary conditions is not the same geometry that existed without the -1 to the f insertion, but instead the geometry that we should be looking at should have a non-trivial angular velocity. What's the angular velocity? So here, this omega that appears, if you follow conventions a little bit, the omega that appears here being equal to 2 pi is a Euclidean angular velocity. If I were to work in terms of Lorentzian angular velocities, I wouldn't have this factor of I. But turning on this -1 to the f doesn't only allow omega times beta to be equal to 2 pi. More broadly, so I'll just denote omega Euclidean just by omega. It more broadly allows omega times beta to be 2 pi times 1 plus 2n, where n is an integer, if j is half integer quantized. Right, you can see here that the n's is multiplied by 4 pi, and 4 pi times a half integer just doesn't produce any additional phase. So the proposal is that if we follow the prescription that we typically follow in gravity of fixing boundary conditions according to what's inserted in the trace, the index with fixed charges qi at any inverse temperature beta should be given by a sum over all these values of n, where I evaluate the action of a black hole that has fixed beta and fixed angular velocity as a function of beta. So this is in the saddle point approximation. So this is the proposal. Because I want to sum over all geometries that are consistent with the boundary conditions. The boundary condition just tells me to insert a -1 to the f. This gives an ambiguity in which what omega is. So in principle, my boundary condition is only defined up to, omega beta being defined up to an integer. And as we still see, the action in the saddle point approximation for all these different values of n will be different. So there are actually physically distinct geometries that satisfy the exact same boundary condition.
Why should minimum like the minimal action of all of this?
You mean, indeed, that's what dominates in the saddle point approximation. Here, maybe let me go through it, because what will happen will be somewhat surprising, which will be that there will only essentially be one value of n contributing here, but not for the reason that you might naively think. I'm just saying that these are all the saddle points. If you want to, typically when we apply the saddle point approximation for an integral, we want to look at all the possible saddles. And in principle, if your integration contour passes through all of them, you have to sum the contribution of all these saddles. Okay, so the
that it's fine. It sounds a little dangerous, right? Because naively, it would go like, okay, nothing should actually depend on n, but then if I do that, I'm going to get it infinity.
No. So actually, the action does depend on n. It will depend on n. And I can give you an analogy. It has nothing to do with gravity. I can give you an analogy of field theory with asymptotically S1 times S3 boundary conditions.
I guess D-brain side, so that you could say that you actually have to do this because that's what the theory wants on both sides.
Yes, in some settings, there's an analogy where people have explicitly seen this sum, and I can at the end I can tell you where, but yeah.
You're looking for that.
Right. Sorry? Exactly, yes. So more broadly, suppose that I didn't want to look at an index. I just wanted to compute the partition function with arbitrary beta omega. It better be that my function that I obtain for the partition function is periodic under shifts of omega by 4 pi over beta. Right? Because if J was truly quantized, this would guarantee that. This is an essentially way of deriving the fact that J is quantized by summing over all possible geometries that fill in the bulk. Good. Okay, so you know what the resulting geometry is. You just take the same black hole that existed at 0 temperature, put it at finite temperature, and turn on an angular velocity. So the simplest black hole that are supersymmetric at 0 temperature are just Reinster-Nordstrom black holes that are extremal. So just have, let's say, a single electric charge. They take exactly this form. But now, when you turn on an angular velocity, the solution becomes a lot more complicated. There's mixing between the components of dt and the spherical components, and the metric becomes a complete mess. So I won't bore you, unless someone really wants to see this. I won't bore you with what the metric of, it's called the Kerr-Newman solution. I won't bore you with what the metric of a Kerr-Newman solution is, but I will tell you what the important result is. So to see the important result, we just need to look at the action of these solutions. And just to give you an example, although this will be a lot broader, I'll just show you what the action is in a beta, the first couple of terms in the leading beta expansion of this action. So we're looking at this action, keeping beta omega fixed, right? We're keeping it equal to this value, and expanding it at large beta just to see what happens as we approach the extremal limit. So at leading order, we obtain minus beta q. This is a normal term. It just gives the Boltzmann weight of the ground state. All the extremal black holes have mass equal to their charge. They can be thought of as the BPS particles. So h minus r is equal to 0. Here r is equal to q. Sorry for the unfortunate notation where q denotes both a supercharge and an actual charge. But this is just the Boltzmann weight of BPS states. Then there's a term which looks like pi q squared. This is the extremal entropy. So this is the analog, the simpler analog of what Strominger and Vafa used to match the string theory answer. And then we now have terms that non-trivially depend on omega. The first of which looks like q cubed over 2 beta times 4 pi squared minus beta omega squared plus higher orders in beta. Okay, so this is the formula for a general Kerr-Newman black hole at any omega in an expansion in beta. And notice that something very special happens when I set beta omega to equal plus or minus 2 pi. So when that happens, the leading term in the 1 over beta expansion drops out. And you could go to the next subleading term. The next subleading term actually is also a polynomial in that depends on 2 pi minus beta omega. You go to the next subleading term, and the thing repeats on and on and on to all orders in beta. And what you find is that for beta omega equal plus or minus 2 pi, the Euclidean action of all these configurations, so, is simply given by minus beta q plus pi q squared. So this is the first signature that the prescription works. Because notice, if in a regular quantum mechanical system, what you have here is that here the action is essentially the free energy of the system. It's just the log of this quantity. So what we should recover is that the associated free energy to a supersymmetric theory, if the associated free energy to an index is just minus beta times the BPS mass of the states, so in this case QR, plus the log of dB minus dF. And this is exactly what we've recovered here. This pi q squared can now be viewed as the logarithm of the difference between bosonic and fermionic states. And moreover, there is another special fact that we will be exploiting in the second part of the talk, which is this geometry has a killing spinner. So previously, so to say that a geometry is supersymmetric, it's just the statement that there exists a killing spinner on that specific geometry. That's typically what people say when a geometry is supersymmetric. And here, the lore was that all the supersymmetric geometries only exist at 0 temperature. They're all the extremal black holes. The actual result now is that you could have geometries that are supersymmetric at absolutely any temperature, as long as you turn on an appropriate angular velocity that mimics a -1 to the f insertion. Now, this is option 1. If I set beta omega to be plus or minus 2 pi, but notice that here I have an infinite number of other saddles. So option 2, what if beta omega is not plus or minus 2 pi, but instead n is different? Plus or minus 2 pi, you can see from here, corresponds to -1 and 0. So what if n is different than -1 and 0? Well, as I was telling you guys before, even just from this leading term in large beta perturbation theory, you can see that the action does not take the form of an index, right? It's minus beta q plus pi q squared plus a term that is that goes like 1 over beta, which is absent in the logarithm of an index. So what happens to these geometries? So action is not good. Not the form of an index. So perhaps the prescription is wrong. Maybe I'll keep it here. Well, what happens, unsurprisingly, usually a killing spinner is associated to the fact that the ADM mass of the system is equal to its BPSR charge. Since this is not the case for the action with any other value of beta omega, you can explicitly check that there is no epsilon that is smooth that satisfies the killing equation. So there are no killing spinners. So at first sight, the absence of a symmetry doesn't seem like an issue. You just have some saddles that have a fermionic symmetry and some saddles that don't. However, it turns out that in the absence of a killing spinners, your gravitational path integral has a set of modes of the gravitino, which are essentially large superdifeomorphisms of the gravitino. They are super partners of the large diffeomorphism generated by partial tau. So it turns out that in these geometries, there exists the set of modes of the gravitino, which are super partners of the partial tau, for which the action is completely independent. Here I'm talking about off shell. So you expand the action in all these modes, and you track how the action depends on these modes of the gravitino. And what happens is that the action is independent of this specific mode of the gravitino. And when you have a path integral over a fermionic mode, where the action is completely independent of that mode, your result will be just an integral over a Grassmann variable, which is 0. So this gives 0. So seemingly, because we have these large superdifeomorphisms, our results, we have some moduli space for the gravitino that gives a 0 answer. However, this is only when our geometry does not have a killing spinner. When our geometry has a killing spinner, what you have to do in the supergravity path integral is that you have to quotient out your path integral by the set of all your isometries, or in this case, super isometries. And it turns out that these modes are exactly the ones that are the super isometries associated to the killing spinner that is seen in these geometries that have beta omega equal to plus or minus 2 pi. So in other words, these geometries this integral gives 0 when beta omega is plus or minus 2 pi. And it gives a non-zero value because you quotient out essentially there's no integral left over. You're just not integrating over the fermionic modes that are associated to that killing spinner. So it gives a non-zero value when beta omega is equal to plus or minus 2 pi, which means that our path integral, even though here we only use the quantum analysis for a single fermionic mode, because that fermionic mode was a 0 mode, it means our index from gravity that we defined as a sum over all saddles n is just given by e to the minus action with a single value of n, namely plus or minus 2 pi, which to leading order in G Newton just gives e to the minus beta q plus pi q squared. So that's exactly the form that we expect for an index. So for this first part of the talk, there are 3 take-home messages. The first is that there is a misconception that only geometries that have 0 temperature are supersymmetric. That's not true. So message 1. Message 1. There exist geometries, on-shell geometries, that satisfy nabla mu epsilon equals 0 for any temperature, for any beta. And those are the ones that contribute to the index, as we've seen here. Message 2. The free energy, so the log of the index, which is given by this differential action, has trivial beta dependence. And log of dB minus dF can be read off as the beta independent piece.
Can you say how you resolve the basic issue that you have?
That's point number 3. That's point number 3. Point number 3. What about the fermionic boundary conditions? I said at the beginning that you could just think of the fermion being periodic on the boundary. What happens with that? Are those boundary conditions just incorrect? They should be equivalent to inserting a -1 to the f. So
the fact that it's not obvious that it's including an index because you're circle.
good. So good. So this all comes down to which circles are contractible in this geometry and which circles aren't contractible. Namely, if you take, if you go close to the black hole horizon, it's okay, it's okay. If you go close to the black hole horizon, around the tau circle, you should take into account the fact that the horizon itself is rotating as you go around the tau circle. That's what rotation means, right? It's as you travel in time, things travel along the phi direction. So the circle that's contractible because of that is not the tau circle by itself. So on a non-rotating background, the circle that was contractible in the tau and phi coordinate was just tau plus beta and keeping phi the same. But now that phi rotates as you travel in tau, implies that the circle that's contractible is this one, the one where as you go beta along the tau circle, you travel phi plus beta omega along the phi circle. You could actually check this explicitly in this metric. So what does this imply for if beta omega is plus or minus 2 pi?
In phi, whichever two plane you put.
Yeah, it's whichever two plane is orthogonal to the angular momentum generator that appeared in this -1 to the f insertion. Good. So it implies that the circle that we should be looking at is the circle in which I not only rotate in tau, but I also rotate in phi once. But this phi for a scalar field, it's also 2 pi periodic. So for scalars, I can make this identification to come back to this identification for an identification of phi. So things seem almost identical. However, that's not true for fermionic fields. So for fermionic fields, what thus happens is they have to be antiperiodic around the contractible circle. So psi, so let's say that there's some fermionic field psi of tau and phi is equal to minus psi and tau plus beta and phi plus 2 pi. But now if you do a 2 pi rotation of this fermionic field, the boundary condition that you recover at infinity, if psi and tau and phi is equal to plus psi of tau plus beta and phi. So this, to begin with, was the boundary condition that we were looking for an index. And of course, we recovered it but we took this different perspective of turning on an angular velocity and seeing the fermionic fields at the end of the day satisfied the right boundary conditions that we wanted all along. So why people missed these configurations is because they took the same geometry and tried to put a periodic fermion instead of trying to find the set of all geometries that accepted a periodic fermion and had a finite size circle at infinity. Okay, so this was part one of the talk. Any questions? Okay, let's go to part two. How do we generalize this? Yeah.
So you say a large fermionic diffeomorphism. The large diffeomorphism means over two things, like part of the gauge group differentiality or a physical.
It means it does not vanish at the asymptotic boundary.
So it's
Yeah,
change.
the physical, yeah, it's a physical change at the asymptotic boundary. And the way to think about it, sorry, I erased it. But the way to think about it is in the following way, acting with this super diffeomorphism that, acting with this super diffeomorphism is kind of like inserting a supercharge in the index. And if you go through the proof of why the index only receives contributions from BPS states, it basically inserts an anti-commutator of two supercharges. And it's kind of similar to the proof that these geometries that have these large super diffeomorphisms that are not gauged by an isometry are non-vanishing. Sorry, give a vanishing contribution to the index.
So like typically a gravitational particle is one where you fix the boundary conditions, right?
Yes.
And so why are you integrating one that doesn't vanish in boundary?
Good. Well, you have to decide what boundary conditions you impose for the gravitino. And here you impose boundary conditions that in some sense preserve supersymmetry. And if your metric is allowed to asymptote to flat space, it turns out that this mode is essentially an allowed mode.
This is more like an extension of optical transforms.
Yeah. All right. So what about more general configurations? How do we generalize this procedure? And instead of taking solutions that we know at zero temperature and giving them finite spin, finite angular velocity, how do we instead work the other way around and try to find configurations that are that preserve supersymmetry, and instead derive the fact that they need to have finite angular velocity. So this allows us, if we work the other way around and try to find the most general configurations that are supersymmetric, we will find a much broader set of solutions, not only these Kerr-Newman black holes, for which you take a black hole and turn on an angular velocity, but a whole plethora of black holes. So let's take the opposite approach and ask, what is the most general geometry that has killing spinners and as a solution to the equations of motion in, let's say, Einstein-Maxwell theory? So it turns out that this problem has actually already been solved. People classified all the solutions of Einstein-Maxwell equations in the 70s that admit killing spinors. So in contrast to just the pure GR solution of trying to find all the solutions to Einstein-Maxwell's equations, or even just Einstein's equations alone, the fact that you have a killing spinor is a very strong constraint. That's because the killing spinor equation, which is here, is linear in the metric. Yeah, you essentially don't have a complicated PDE to solve. So the most general solution that asymptotes to flat space that has a killing spinor takes the following form. So this is a result found by Todd in the 70s. Is the following. The metric takes this form of 1 over u times u tilde d tau plus omega I dxi squared plus u tilde dx squared. So here x is an R free, is a flat base space. And this function u, but if the killing spinor equation is solved, this function u and u tilde turn out to have to satisfy a constraint, which is that u and u tilde are harmonic functions on base space. So this u and u tilde depend on x vector. So it's just a 3D base space with some factor, where as we go in time, we can also travel in this base space due to this form, omega I, which is like a 1 form on the base space, that can be viewed as inducing some rotation as we travel in time, depending on what omega is. So let me just write, so u and u tilde are forced to be harmonic. And let me just write what the equation of motion implies for omega and for the field strength. It implies that star d omega. Here, star d is defined on this base space, not in the 4D space, is u tilde. Let me write it explicitly. Epsilon I j k partial k omega is u tilde partial iu minus u partial iu tilde. And f0I is 1/2 partial I 1 over u plus 1 over u tilde. And fij is minus 1 over 2 square root of the metric. I'll explain why I wrote this formulas in a second. I'm not a big fan of writing formulas, but these formulas actually give you some good intuition about how the space-time looks like. Okay. So the fact that u is harmonic implies that u and u tilde can be written as 1 plus a sum of poles over the base space at some location xi with some residues ai, and the same for u tilde. Yes. It's like a generalization of Taubnut.
I guess you get Taubnut instead of equal to 1.
You set u tilde. Yeah, exactly. Yeah. Good. So notice just 2 things, that if u and u tilde are identical, then all these fields vanish. Sorry, this one and this one. So omega becomes 0 just because it involves a difference of u tilde du and u du tilde. And the magnetic field Fij also vanishes because it involves a difference of 1 over u minus 1 over u tilde. So maybe I forgot to say that this is the most general solution to the killing spinor equations that has asymptotically has an electric charge. But if u and u tilde are different than each other, this means that Fij becomes non-zero and omega becomes non-zero. So the fact that omega is non-zero means that as we're traveling through base space, there is indeed some rotation that, as you travel through time, there's indeed some rotation that occurs through base space. And the fact that Fij is non-zero also makes sense. Fij is like a magnetic field. It's because if I have electric charges, and I give electric charges some rotation, that induces a magnetic field, right? So this is another signature of the fact that even though asymptotically the overall flux is electric, I can have non-zero magnetic field due to the rotation. Okay, so this is the most general solution, but Todd only solved the equation locally. We need to make sure that this, in order to make sure that it's a saddle in the gravitational path integral, we need to make sure that the solution is globally smooth. So where could problems arise? Well, problems can arise if you look at where the metric is ill-defined, right? Namely, it can arise at the poles of u and u tilde. So smoothness. Yeah. The electric, you mean magnetic fluxes? Yes. I will also talk about that later as well. Yeah. That's kind of part 3 if we get there. Okay, so smoothness. So we want to make sure that this metric is actually not singular at these xi or xi tildes. So for now, let's assume that I'm interested in this case that's slightly more complicated, where u and u tilde are different than each other. So let's assume that xi is different than xi tilde. I can use this equation. I can act with a partial on it. On the right-hand side, I essentially recover the Laplacians of u, or Laplacian of u tilde, which is either 0 or a delta function at the sources. So I can use that equation in conjunction with Stokes' theorem to write what the integral over omega is. So here's, well, let's say the poles of u, a pole of u. And here is a pole of u tilde. So I can use Stokes' theorem, assuming that omega vanishes at infinity, which indeed it does at on this solution, to write what integral of omega is along an infinitesimal circle along a tube that separates the blue and red point. So it's just applying differential here and using this fact. Integral of omega along this S1 is equal, so this is an integral on base space, is equal to 4 pi ai times u tilde. The way to most easily see this is, you see when I act with a differential here, I pick up the delta function that appears in the Laplacian that has coefficient ai, and it's multiplied by whatever value, here, whatever value u tilde has at that point. So this is if, so u tilde evaluated at xi. So notice that I'm evaluating the function u tilde at the poles of the function u. So this is a finite value in principle. So naively, you might think that this makes the geometry singular, because it means that I have an integral over a one form over an infinitesimal circle that is finite. So omega, therefore, along this circle in the directions parallel to this circle has to blow up. So omega blows up. Problem? Well, it's only a singularity if you cannot get rid of it through a coordinate transformation. So by the way, the same thing happens with the integral over omega along a circle that's close to the red pole. Instead, integral over, let's call this circle S1 prime or S1 tilde over omega in that circle gives 4 pi ai tilde u evaluated at x tilde I. So it's only a singularity if I cannot get rid of it through a coordinate transformation. The way in which you should view it is exactly how in gauge theory, if you have a Dirac string stretching between a charge and an anti-charge, your gauge field is only singular if you cannot get or move that Dirac string around through a gauge transformation. So we can perform the following coordinate change. So T can, if we change T by some arbitrary function on the base space, so some arbitrary function of xi, then omega I would change by omega I plus partial I lambda. So it would change exactly like a gauge field, where lambda is the gauge parameterizes the gauge transformation. So I can choose T to get rid of this integral, to make this integral over omega be 0 after a change of coordinates. I can choose T to go like T minus, oh, sorry, I made a mistake. There's an extra sign here due to the direction of integration. Anyway, you can change T by T to minus 2u evaluated x tilde 8 tilde phi close to x equals xj, and T to minus 2u tilde of x times a, this is aj, aj phi close to x equals xi. So here phi is the angular direction. So you take the circle, phi is the angular direction that parametrizes the circle. Okay, so these transformations seem somewhat peculiar, but notice that actually if my metric was Lorentzian, so here I wrote the metric in Euclidean signature, but if my metric was Lorentzian, these transformations would actually be illegal for the following reason. Phi goes to phi plus 2, phi should be identified with phi plus 2 pi as a point, at least for bosonic fields. So this coordinate transformation would map, if phi is equal to 2 pi here, it would map phi equals 0 and phi equal to pi to two different points on the space-time. So therefore, this coordinate transformation is inconsistent with the periodicity of phi. So inconsistent with phi going to phi plus 2 pi, unless T itself is periodic, which is exactly the case in Euclidean signature. So if T is periodic, and I want to make this identification, I can make this identification such that when I do a rotation by 2 pi and phi, it results in a rotation in tau by a factor of beta. So this sets what this coefficient is. So from here, we find okay. U tilde times A, U tilde at each xj times aj is equal to beta over 4 pi. And U of x tilde of j times A tilde j is also equal to beta over 4 pi. This should be an equation that applies at any poles of the function u and u tilde. Now, the cute thing is, okay, so this is Euclidean, Lorentzian. The only solution that's smooth and has xi different than xi tilde is u tilde times a, u tilde of xj times a, j is equal to 0 for any j. And this makes the solution trivial. The only solution are all the a's equal 0, u and u tilde are both 1. That's literally just flat space, right? Or the other option is for xi to be equal to xi tilde. If xi is equal to xi tilde, then Stokes' theorem, the way in which I apply Stokes' theorem here is incorrect, actually. So the other option is that for u to be equal to u tilde, in which case you obtain a class of solutions called the extremal multi-center solutions. So the name that people usually give them is Majumdar-Papapetrou solutions. So let's go back to the Euclidean one, though. We can now write this condition, u tilde times a. It's convenient to rewrite it in terms of the value of omega on each one of these Dirac strings. So the value of omega determines the angular velocity with which this string rotates. And it turns out that this u tilde times omega, it's precisely equal to 1 over 2 omega, the value of the value of the one form omega along this direction, along the direction that surrounds the Dirac string that connects the blue and red points. The important thing, okay, you derive this mathematical equation. What this tells you, and this applies for any j. So omega, you could write your field omega roughly as omega times d phi. So it's like the angular velocity that you have on the space-time that this Dirac string, the angular velocity with which this Dirac string rotates. So this equality, together with the smoothness conditions, implies the following, that beta omega is once again equal to 2 pi. Which means, let's summarize where we started and where we ended. We started with the most general geometry that has killing spinners and satisfies the equations of motion. And what we've derived is that the only solutions have angular velocities for all the Dirac strings in these geometries to be equal to 2 pi over beta, which is precisely the angular velocity that was needed to compute an index. In other words, we started with a killing spinner and we derived the angular velocity that computes an index. The only thing is now we derived a much broader set of solutions. So in fact, let's just give you an example. So I told you before that I'm not going to write the Kerr-Newman metric because it's too ugly. I'll actually write it down now because now it's actually very nice. No, besides this, there's no constraints. So whatever, this is a set of, if I have n poles in U, this is an n poles in U tilde. This is a set of 2n equations. Yes, in order for the space-time to be asymptotically flat, they have to be equal. And the smoothness conditions also, Taub-Knot does not have a topology asymptotically that looks like R3 times S1. That's precisely because, well,
Are you worried about the quotient?
yes, exactly. That's precisely because Taub-Knot, as you said, has no poles in U tilde. We just saw that each pole in U, from each pole in U, there's a Dirac string starting. The point is that in Taub-Knot, the Dirac string doesn't end. It goes all the way off to infinity. So if I measure integral of omega around that Dirac string, even at infinity, I'll obtain a non-zero answer. And that signals the fact that even though the space is locally asymptotically flat, the topology is not exactly that of R3 times S1.
If I thought of it in M theory,
Okay.
what where the center of the Taub-Knot would be D6 frame?
What
What are the other?
You mean what are?
What are we describing? What is that?
Well,
I mean, right.
I think, roughly speaking, it's so the poles in Taub-Knot would be like D6 branes, right? I think here, because you turn on this angular velocity, probably the branes spread out a little bit. And yeah, I can't exactly tell. I don't have a good physical picture at that interpolates between weak string coupling and strong string coupling. And I think this picture of the Taub-Knot being like a stack of branes is like the weak string theory picture, right? I guess the point is that with the -1 to the f insertion, things are slightly more non-trivial. Let me just let me just quickly write this example. So let's say Q is equal to 1 plus A1 over x minus x1. So U and U tilde should, let's say that they have each have a single pole. There's only two constraints, right? Because this applies for any j, but j only runs over from 0 to 1. Sorry, from 1 to 1. The constraint looks like A1 times 1 plus A1 tilde over x1 minus x tilde 1 is equal to beta over 4 pi. The other constraint looks almost the same. It looks like A tilde 1 times 1 plus A1 over x minus x1 minus x tilde 1 is equal to also beta over 4 pi. From here, you can see that A1 is equal to A1 tilde. And if you look at what the value of the electromagnetic field is, you'll see that A1 and A1 tilde are actually charges. They are equal to the overall electric charge that you would see at infinity. You could compute the ADM mass of the solution. You'll find that it's equal to exactly A1 or A1 plus A1 tilde over 2, I think, which is exactly Q. So you're exactly saturating the BPS mass. That's, of course, should be the case because we started out by imposing that our geometry has a killing spinor. But this solution also determines what the distance between these two poles is. It tells you that the distance between x1 and x1 tilde is some beta-dependent function. And this turns out, so if you plug U1, U, and U tilde into the metric that I wrote previously, this very simple u and u tilde, and you perform a change of coordinates where you slice your base space into spheres, then the metric that you get is exactly the Kerr-Newman metric. From part 1 of the talk. Oh, you just take u and u tilde to take this form. So have a single pole each. You plug it into the metric that I mentioned previously. The metric is defined in terms of this base space, but you could write the base space in a radial coordinate. And then with like a very trivial change of coordinates from that radial coordinate, you get exactly the Kerr-Newman metric. And the Dirac string, so here the Dirac string is localized on a line.
It's driving this which somehow is supersymmetric because you turn on something more.
But I think this is not exactly so. Like, I think there's a distinction here between the M theory large charge and the large charge that we're describing.
No, okay.
What I think is that in an equal to supergravity case, when we study this type of solution, we can actually develop these large charges in the direction of like D2 charge. So
Yeah.
Like, these not what we mean by large charge is like gravitational large charge.
Yeah, perhaps this will come up in when we go over the generalization of the attractor solution, because there it's a bit different than here because you have these scalar fields turned on. It turns out if you turn on, let's say, D6 and D2 charges, that will also induce a non-zero field associated to D4 and D0 charges. And that's precisely, due to the fact that if you turn on electric charges that are rotating, you also induce a magnetic field.
Sure.
Yeah. So that's why, yeah. Right. But the overall magnetic flux is 0, even though the magnetic field is not 0. Good. So this is exactly the Kerr-Newman metric that I mentioned previously. The only thing that's a bit funny is that the Dirac string here that's stretched in between the points x1 and x1 tilde after this coordinate transformation that I mentioned actually gets mapped to a 2 surface. So here it's a line, but the coordinate transformation that you do to go to Kerr-Newman is actually singular on that line, and the Dirac string in this geometry is actually the same as the horizon of the Kerr-Newman black hole. And the direction of this Dirac string sets the direction in which the Kerr-Newman black hole rotates. And the poles of the function u and u tilde simply become the north and south pole of the black hole after this transformation. Good. The thing to keep in mind is that this Dirac string, even though it's like it seems like it's a line, if you actually measure the proper distance, the proper length along a circle that surrounds the Dirac string, that proper length is actually finite. It doesn't go to 0 as the circle size goes to 0, which indicates that even though it looks like a string in the metric, it's actually a blown up surface. Okay, so perhaps let me just tell you one more thing surprising in this black hole, which is let's now compute, since we know that this Dirac string is like the horizon of this black hole, let's now compute the area of the black hole, which previously had the interpretation of entropy, right? So the area actually takes a very, very simple formula. it's just beta times x1 minus x1 tilde. And we can also compute, so the area has non-trivial dependence on the temperature, indicating that the area couldn't possibly be the index. X1 minus x1 tilde, you see we solved it from the smoothness constraint. It also has complicated dependence on the temperature. So the area is some non-linear function of the temperature, in contrast to the log of the index, which should be linear in beta. However, beta omega j in this geometry, beta omega is just 2 pi. And we can compute j classically. We find that it's given by minus q times x1 minus x1 tilde over 2. So this term gives in total minus pi q x1 minus x1 tilde. Good. So if we add whenever we're computing a free energy, we should add an entropy to whatever beta omega j term we turned on in order to compute the free energy. So the free energy of this system, if I really view the area as an entropy, is given by beta times x1 minus x1 tilde plus this beta omega j, which is minus 4 pi, sorry, this is 2q x1 minus x1 tilde, minus 4 pi q x1 minus x1 tilde. So now I can use the smoothness solution for x1 minus x1 tilde, and notice that the beta, minus beta q. Notice that, so I'll continue here, that the beta dependence completely cancels once you insert what x1 minus x1 tilde is. And you get that the free energy of the ensemble is equal to pi q squared minus beta q, which was exactly the action that we derived initially. So in other words, even though the area itself, the area of the black hole or the associated entropy of the black hole seems to have a non-trivial temperature dependence, once you work in the correct ensemble and derive the free and add the correct beta omega j term, you precisely recover the free energy associated with an index that we've also derived from the action. And we can think of this result. Sorry, let's see how much time I have. Okay, 20 minutes. We can think of this result as an analog of the attractor mechanism in the following sense. The attractor mechanism just tells you that the properties of a black hole are independent of their boundary conditions. Here, we're finding that the index takes this very rigid form in terms of its beta dependence. So beta is like an asymptotic moduli that you vary. And whatever beta is, the free energy, namely, if you look at the entropy associated to the free energy. So if you look at df db, d beta, beta at this is beta independent. In the same way in which previously, in the attractor mechanism, the area of a black hole was independent of how you varied the moduli. Here, this quantity is independent of beta, which as a consequence gives a nice form for the index. Now, one last thing that I want to mention about these solutions. Yes. Yeah.
What's the integral of d omega around here?
D omega.
So omega is when the RR one. Sorry, you have to ask what this is an M series, right? So that's
Omega is like the angular velocity.
That's the derivative charge.
Omega, the integral to omega.
Well, I think if you reduce it to the string, it's gonna be omega is just this is definitely an M series solution, right?
Yes, 100%. Yes.
The question is what does it describe? I mean, it looks like you have two sets of D6 brains.
Yeah, like
I like to say that D6 anti-D6, but there's no line signs anyway.
Yes, so I think it's two sets of D6 brains.
But there's no direct strings.
Yes, sorry. I didn't finish. Two sets of D6 brains that also have non-trivial D6, D0 charge.
That's right.
One, the North Pole has plus D0 charge. The South Pole has minus D0 charge. Because in some sense, you can view this North and South Pole, they have their own electric field, but you could view them as a dipole for the magnetic field. So you could associate some magnetic charge at each one of these poles, and it will correctly reproduce the magnetic field away from the black hole, even though again the magnetic flux is 0. So that's what I would venture to say the.
So if you were to compactify this on 6 bars to get a completely honest new model of a black hole, then
Right. Yeah, I think that's true. Okay, so let me just say that in general, so even though these solutions are somewhat complicated, right? It's not as if the space-time looks like an independent union of the poles of U and the poles of U tilde. The action, when you evaluate it, and this is just some algebraic mess, but when you evaluate it, you find that the poles, the residues of these poles completely decouple. In the following sense, you find that the action is pi over 2 sum over ai squared sum over a tilde I squared minus beta over 2 sum over ai plus sum over ai tilde. So you give me the charges of these north and south poles, and this is their overall contribution of this configuration at leading order in G Newton to the index. So the exponential of this is the leading order contribution to G Newton, where notice very importantly, the factors of A and A tilde completely factorized. So in some sense, this is the same if I think about individual indices being associated to each one of these charges, A and A tilde, because this goes in an exponential, it's as if the index of this new solution is a product of individual indices, which is somewhat reminiscent of this Kontsevich-Soibelman formula, where the jump in an index is proportional to the product of two individual indices. Okay?
sorry, there are no jumps, right?
There are no jumps. Yeah, okay. So maybe there is no time today, but now let's actually go to the initial equality in the talk. All these solutions are solutions in Einstein-Maxwell theory, which can be, uplifted to solutions in supergravity, where you turn off all the fields in all vector multiplets. But what happens for the black holes that are relevant in string theory is that some of the vector fields in the various supermultiplets that are in which the graviton is not part of, from the n=2 perspective, are turned on. So, and in turn, turning on the vector fields in those supermultiplets induces a non-zero value for the scalars in these solutions. So in supergravity, supermultiplets have vector supermultiplets. The bosonic content has scalars and gauge fields. The fact that you turn on the gauge field ends up meaning that you also have to turn on a non-trivial profile for the scalars. So these solutions are the ones where the scalars are turned off. So what about the actual black holes in string theory? Maybe I'll make, since there's not a lot of, actually, I'll say after the talk. But yeah, so these are.
Wait, this is a black hole.
It's a black hole in string theory, but it's not the one whose index was computed by, let's say, Strominger and Vaslav.
No, it's not. It looks better.
Yeah, it's simpler. It has less charges. Yeah, but we can also study those, right? So these are what happens. There's these solutions called the attractor solutions that Strominger, Ferrara, and Kalos found, and the generalized multi-center solution. Enter solutions that Denef, Bates, and Moore found. Okay, so these are a bit of a mess as well, but it turns out that they also have, by also starting with the same approach, where we impose that the geometry has killing spinors and satisfies the equations of motion now in in supergravity with all the supermultiplets turned on, we can still find the most general solution. And once again, we find that the most general solution in Euclidean signature that has killing spinors has beta omega equal to plus or minus 2 pi. So once again, all the solutions that we find are exactly the ones that should be computing the index in supergravity.
Was there magnetic flux? You said
There's no magnetic flux. There's magnetic field. There's no physical sphere. There's no actual sphere. By physical sphere, I mean actual sphere in the geometry that doesn't have singular points, that has integral of f be non-zero.
But around that sphere that you have integral of f.
Which two sphere? Perhaps let me mention something that might be a bit confusing,
I mean,
which is that if you.
Microscopic calculation, they're both.
Yeah, I agree with that. I don't exactly know what it is though. So between the North and South Pole, if you naively take the sphere that surrounds the North Pole, this has non-zero magnetic flux. However, geometrically, this is not actually a sphere because, as I said, if you look at the proper length of a tiny circle that surrounds this Dirac string, this proper length is finite, meaning that the sphere doesn't actually close. So that's why I wouldn't immediately say, oh yeah, you just give some magnetic, you put some magnetic monopole here and some anti-magnetic monopole here, and that automatically generates this solution. It's because this Dirac string, which actually is the horizon of the black hole, is kind of a coordinate singularity. And it's not a genuine singularity, it's just a coordinate singularity. Yeah, maybe I'll just end by saying that these solutions also satisfy beta omega equal plus or minus 2 pi. It's no longer true that the scalars, so in the typical attractor mechanism, what happened was that the area of the black hole and the scalars evaluated at the horizon only ended up depending on the charges of the black hole instead of on the asymptotic boundary conditions that you fix at infinity for the scalars. And good. So that's not the case here. Instead, the scalars have a non-trivial profile on this. There's an analog of this Dirac string that still represents the horizon of the black hole. The scalars vary along the Dirac string. However, if you compute the action of these solutions, the action is still completely independent of what the asymptotic moduli are. and moreover, takes exactly the form of an index. So it's linear in beta, and the entropy, the log dB minus dF, exactly matches the area of the black hole that Denef and Moore found. And this can also be generalized for multi-center solutions. And there, what's very interesting is that we had these smoothness constraints, which have an analog, so they look very much analogous. Did I erase that equation? Maybe I did. Yeah, there's the smoothness constraint that I wrote down for the multi-center solutions without gauge fields turned on. There's an analog of those equations now in the multi-center geometries that have scalars turned on. And the interesting thing that we find is that as we vary the asymptotic values of the scalars, some of the solutions, we lose some of the solutions to the smoothness equations. They just vanish as we vary them, vary the values of the scalars, and they vanish precisely on the walls of marginal stability that Denef and Moore found in the past. So that means that we expect that even this index computed from gravity loses some of its saddle point solutions as you vary the moduli, which is exactly this phenomenon of wall crossing. Moreover, because now we have the action of these solutions, then Denef and Moore only said roughly that the overall entropy should be the sum of all the areas of the black holes, which didn't have any a priori reasoning, but we actually have the action. So we actually have a saddle point argument of how much the index changes as you go through the wall of marginal stability. And at least at first sight, where this is still a work in progress, it agrees with the product of two independent indices, just like in the Consevi-Soibelman formula. So yeah, the long-term plan is to use the gravitational path integral for, I don't know how long-term, but the plan is to use the gravitational path integral to try to fully reproduce all the math in that formula. Maybe let me mention, yeah, I think I'm referring to something that the primitive and semi-primitive Consevi-Soibelman formula. Let me just say another surprising consequence for our own universe, which is, okay, we don't live in a theory of n equal 2 supergravity or n equal 4 or n equal 8, but these saddles that we've studied still exist for black holes in our own universe. Namely, you can try to compute, yeah, outlook 1 was multi-center black holes and the Consevi-Soibelman formula. Outlook 2, I'll name it somewhat courageously, Susie without Susie. So you can still try to compute trace minus 1 to the f, e to the minus beta h, just in a gravitational theory that is not supersymmetric, like the one that seemingly described the low energy theory in our own universe. And the same saddles that dominated the ensemble when you computed a supersymmetric index surprisingly still dominate in this case, which means that to leading order in G Newton, you could actually check this, the trace of minus 1 to the f e to the minus beta h in any gravitational theory that has fermionic degrees of freedom and is well approximated by Einstein gravity at low energies is just e to the pi q squared. So this is the trace in a sector of fixed gauge charge, e to the pi q squared minus beta q plus things that are subleading in q, roughly. So this means that most states in a sector, most black hole states in a sector of fixed charge, even in a theory that is not supersymmetric, have approximate superpartners. The fact that this is beta, that this is only linear in beta, is precisely the statement that anything that has energy above the BPS energy gives no contributions to the index, so it cancels. This implies that perhaps SUSY is approximately conserved at energies where, these black holes live, so at energies above m Planck, even in our own universe. And this just follows from consistency with our low energy gravitational theory.
Here, the gravitational here has no supersymmetry at all.
No supersymmetry at all.
Well, maybe the low line space have fewer degeneracies and stuff above somehow doesn't. I mean, the actual black hole dominates, and then
yes,
like very little. Why wouldn't that be?
Yeah. So you might expect. Yeah. So maybe the better statement is let Laplace.
How could that be? For which reason?
Right. So maybe let's look at the Laplace transform of this statement. So the Laplace transform, if this was an exact formula, it would be that trace of -1, that trace Q in a sector with fixed energy of -1 to the F is equal to basically delta function for E equal Q. So the statement is this is approximately true up to subleading corrections in 1 over Q. Which means that if I go to any energy, naively, most black hole states at any energies will have, most bosonic black hole states at any energy will have an equal number of fermionic black hole states at that energy as well. So the fact, this is the mathematical problem that I think one should address to make this rigorous. The question is, if an index takes this form, so if an index is only, the log of an index is linear in beta up to some epsilon error, what does this imply for the norm of different relations of this in the SUSY algebra? So for instance, what does this imply for the norm of the commutator between H and some operator Q that goes between bosonic and fermionic black hole microstates? Perhaps this is also bounded by the same Q1 over Q, by the same epsilon, through which this index is only linearly dependent on beta. So I don't know. This the result just from the gravitational perspective, even though we didn't work in a theory of supergravity, it seems that black holes intrinsically still want to have an equal number of states between bosonic and fermionic black holes at the same energy level. So this is just the gravitational result. The only assumption, maybe let me just repeat that in case it's unclear. The only assumption here is that -1 to the F acts non-trivially on the Hilbert space, which means that there are fermionic states in your theory. So of course, you could have asked, what if you...
Take that form.
Sorry?
What is the argument that is the answer you get?
Because this is the dominant saddle. So the same saddle that we found in the beginning of the talk, the supersymmetric one. Sorry?
That part's not about.
The part does not rely, yeah. The fact that a saddle has a killing spinner does not imply, does not rely on the theory that the underlying theory that you work in is a supergravity theory. So it's just that the leading saddle that computes this ensemble has this feature that it has a killing spinner, whether you have supersymmetry or not in your underlying theory. So we, right. We checked the contribution of other saddles, and they're all subleading. Yeah, there was a recent paper by Turiachi and Chen that studied even other saddles that were somewhat more exotic, and they also only found subleading contributions. So it seems to be true at leading order. I don't know. Yeah, it's well, I guess it's the same question. You know, the answering. Oh, did you study all the saddles? You could ask that for the partition function as well, right? Like, how did you know that the partition function was dominated by a black hole, even in ADS-CFT? It's an assumption that there's no absolutely crazy saddles that have no spherical symmetry that no one could write down that are not dominating, right? So with the same. Oh, and by the way, this is
particularly surprising. So I
right. This is true also in ADS. You can compute the same quantity in ADS. You also find that the supersymmetric saddle is leading, and there is some field theory arguments by Schiffman that suggests that a large N theory, like large N adjoint QCD, which should have a holographic dual which maybe is not supersymmetric, has this feature that at high energies you have an equal number of bosonic and fermionic states within an energy window. But I find that argument a bit sketchy, but the argument from gravity is seems fairly robust as long as you trust that this is your leading saddle.
So what would be like the higher level I could find it could possibly be?
The argument, but again, I don't know, unfortunately, how to make it concrete, is that the theory, the ultimate UV completion that you're talking about is a superstring theory. And that the signature, even though you're explicitly breaking SUSY through the choice of internal space, somehow for the very high energy states, it's yeah, that's the very simple, and your gravitational description is valid for black holes whose mass is much higher than m Planck. So from a field theory point of view, it's saying that SUSY is approximately restored at energy scales that are much larger than m Planck.
Okay.
Okay, and outlook 3 is that these solutions allow us the opportunity to do supergravity localization for a much larger set of geometries or for a much larger set of boundary conditions. Yeah, we hope to do that in the future, just to localize the index directly. Maybe I should just, as a last outlook 4, finally mention that it would be interesting to take this argument and study ADS-CFT away from the decoupling limit. So notice that in the beginning of the talk, the common pattern in all these solutions is that we're taking a zero temperature solution and putting it at arbitrary temperature and computing an index, but at the same time turning an angular velocity. Here, ADS-CFT itself is a zero temperature solution in the sense that you start out with 10D or 11D supergravity and look at an extremal black brane solution, which has an ADS-D times some internal space for like ADS-5 times S5. Here, you can instead study the index in 10D supergravity by turning on an angular velocity for the black brane and looking at arbitrary temperature. And because the index takes this form that is basically independent of beta, it means that whatever result that's supersymmetric that you recover in ADS-CFT and the limit beta goes to infinity, you should also be able to recover just in asymptotically 10D flat space with these new boundary conditions. So it's kind of interesting because you now have a single theory of supergravity, which in principle, depending on the boundary conditions that you impose, could recover indices in you know, a variety of CFTs across a variety of dimensions. Like you can impose fluxes at the asymptotic 10D boundary that corresponds to a black brane that has a throw that's ADS5 times S5. But you could also look at a black brane that has a throw that's ADS3 times S3 times T4. And you know, they're both in the same theory of supergravity. The difference is just the asymptotic boundary conditions. So somehow it would be a theory of supergravity that would know a lot about the math of all the indices of all the CFTs at the same time. So I'll end there.
What about the last point? Is the black
Sorry?
Like,
No, not as far as I can tell.
yeah,
So there are some rotating black brane solutions that people studied in passing. But I think the question is, at least for those black brane solutions, what happens if you turn omega equal to this 2 pi over beta? Does somehow a killing spinner still arise, and does the story repeat itself? The other thing that I should mention is that these black brane solutions sometimes are also, there's families of black brane, of multi-black brane solutions.
The black brane graph language is the language we potency, right? And then we understood all brains, they're not black brane.
I guess I'm just using archaic language. I don't know. They're just the solutions that have a throat that's asymptotically ADS5 times S5. I thought people still call it, how would you call it?
Thought it all the black brains were shown to be brains. And it's brains or D brains, that's it.
Right. Yeah, it depends again on which flux you turn on at infinity. Right. Yeah, it's not a brane anymore, I think, if you turn on a finite temperature, as in you can't isolate the branes. Right. Maybe let me just say one final point to your question, which is that these solutions have also been expressed in terms of harmonic functions. So just like the Majumdar-Papapetru solutions that existed at 0 temperature were expressed as in terms of harmonic functions. So I kind of suspect that there is a generalization that involves rotations and rotations determined by a more general set of harmonic functions that would kind of look like the generalization of the multi-center solution that we had to the finite temperature multi-center solution that we found. Yeah, so maybe let me just draw an analogy again. So all these extremal black holes, literally all the things that I listed, I think, have a region of the space-time near the horizon that looks like ADS2 times S2. Even these multi-center ones, if you zoom in close to each one of their horizon in these Van F. Moore solutions, or even the older multi-center solutions, they all look like ADS2 times S2, just like, you know, maybe I shouldn't call it black brane solution, but that solution looks like ADS5 times S5. But once we turn on a temperature and arbitrary angular velocity, the ADS2 times S2 component of the space completely disappears. So just like if we worked in 10D supergravity, the ADS5 times S5 portion of the space, we suspect that it also completely disappears. Anyway, that's yeah, so I think this would actually be somewhat of an example of flat space holography in a SUSY sector. Any other questions?
F minus beta, DFT beta, like beta independent.
Uh-huh.
Only that you also want it to be equal to the area of the extreme of that, right?
Yes, that we don't.
You can compute and check it. Is there an abstract?
We don't know of an abstract argument. No, no. Maybe in some sense, these solutions, when you take beta to infinity, even though they have non-trivial rotation, somehow become the extremal black hole. Yeah. It has. Yeah. It also has the right area. You mean if you plug this in here? Yeah, exactly. And take beta to infinity, it just becomes the area of a big extremal black hole. It's a bit, the beta going to infinity limit is always somewhat singular. So it's a bit hard to tell. It does follow from the fact that there's a killing spinner. What he was, I think, asking is whether it's always the case that this factor of pi q squared, or whatever factor that is not linear in beta, whether that always agrees with the area of an extremal black hole. And that I don't think we know. I don't know if Jan agrees or disagrees, but I don't think we know a general argument for.
Not like an abstract.
Yeah. We computed in a. Yeah, it's also. Yeah, I don't know why people would have thought that the entropy of a multi-center solution would just be a sum over areas, but we do find that. So.
In some sense, our computation, you could view it as the reason for why the extremal entropy actually captures something related to the.
Yes, exactly.
I mean, I thought it was because I thought it was general.
Yeah, but from a path integral perspective, it's not at all clear. Yeah, I don't know.
But the indices.
Right. Okay. Thanks a lot.
Let's thank Luca again. Take local speakers off.
It's not a problem.
You're most welcome to join us on any other platform here.
Oh, yeah.